Today I will discuss about complex integration. Now the properties of analytic function are very much related to integration of complex function. So the complex integration nextly bring out the property of analytic function. So complex integration. Let f of AB tends to C be a continuous function and where here AB is closed and bounded interval. And now let ft equals to ut plus I bt. Now f is a function of real parameter t, so it is separated into real and imaginary part. And integration of a to b ft dt equals to a to b ut dt plus I a to b vt dt. Right. Let's see where ft defined in terms of Riemann integral that we know, and see some example. Let us see some example. T cos t plus I t sin t, where t in between 2 pi to 4 pi, right? And integration of 2 pi to 4 pi ft dt, let's separate from imaginary part and real part. 2 pi to 4 pi integration of t cos t dt plus I 2 pi to 4 pi integration of t sin t dt, which t cos t sin t and 2 pi to 4 pi minus, this is real part and this is the imaginary part, which sin t is minus cos t, and t equals to, and t integration of t equals to 1. Let's sin t 2 pi to 4 pi, which tends to 0, and cos t 2 pi to 4 pi plus I minus 4 pi plus 2 pi plus cos minus of integration of sin cos t sin t, which is 2 pi to 4 pi. This refers to 0 plus I minus 2 pi, which is equals to minus 2 pi I. Right. And let's see one of another example with 0 to 2 pi integration of e power I mt and into e power minus I nt dt, which 0 when m equals to n and 2 pi when m not equals to n, and here is m equals to n. It's an easy exercise using the definition, and this property actually makes e to the power imt the orthogonal property from certain vector space. And we have seen this type of an integral. Next, what to want to define what is called a Cantor integral, which is called Cantor integral. And we have a complex variable. We would like to define its integral over piece of spring or curve in the complex plane, where curve has certain property, so it's directly curve. So we here to contours. What is contours? Contours, a curve of gamma with parameter of interval AB is a continuous function of gamma a to b tends to c. Right. Let's see another example. Gamma 2t equals to t plus I sin 2 pi t, where t in between 0 to 1. So this started 0 and v2 and gamma 2 trace the sine curve in the complex plane. There the real axis is acting on the graph, right? Here the real axis is acting on the graph of the sine curve, and where v2 0 equals to 0 plus I sin 0 equals to 0, and where gamma 2 1 by 4th of gamma 2, which is equals to 1 by 4 plus I sin pi by 4, which is equals to 1 by 4 if then I, right? And let's see gamma 2 of half plus I sin pi, which is equals to half, right? Here is half and 1 here, gamma 2 of 1 by 4, right? And in this way gamma 2 of half equals to half and gamma 2 of 1 equals to 1 plus I 0, which is equals to 1. So gamma 2 started the origin in the complex plane at time t equals to half, right? Yeah. And here this point, so the particle start here to travel by gamma 2, and write down this manner. Let us see gamma 3 equals to gamma 3t, which is equals to 1 minus t plus I sin 2 pi 1 minus t. So t tends to t in between 0 to 1. In this manner, gamma 3 0 equals to 1 plus sin 2 pi by 0, which is equals to 1, and gamma 3 of half 1 by 4th equals to 3 by 4th minus 1. Then gamma 3 3 by 4 equals to 1 by 4 plus I. In this way gamma 3 1 equals to 0. So when we try to trace gamma 3 by the definition of curve with a parameter, 0 to 1 and look at the picture when we try to visualize gamma 3. Look this picture, right? Then a curve has an induced direction due to the increasing value of a parameter interval in its parameter interval. When the parameter increase in that parameter interval, that induced direction of curve. So here graphically or visualization, the direction refers to the direction of the curve and range of the complex plane.